All right, guys, let's get started. I assume that you can see my screen and that you can hear me. If not, please let me know. My name is Daria. I'm data solution architect with Provectus, and last several years, I'm basically working full-time on helping our clients to build different data-related solutions, data lakes, data platforms, data warehouses, etc. And many of these cases, we have joined our clients and we have built the platforms from scratch, our solutions on a greenfield. But this particular case and this client that I'm going to walk you through today was a different thing. We joined when they already had their own pipelines implementation, infrastructure, and architecture in place. And our challenging task was to redesign, re-architecture, examine what they have, and try to reduce the processing time from hours to minutes. And for those of you who believe that data engineering work is rather simple and boring and only about bringing data from database to S3, I'm not going to try to convince you, but I hope that at least I will highlight some of the fun things that can happen. And in our case, we were able to achieve the goal of reducing the processing time with help of discrete math. And I'm going to tell you how we did it today. So in terms of the content, first, I want to make sure that we all are on the same page in terms of the domain. And the domain here today is EdTech. So it stands for advertising technology. And I'm going to walk you through some of the main characters that play their roles in EdTech and where our particular client is in this domain and what basically their challenge was. Then I'm going to deep dive into their initial architecture that we saw when we just joined the project. Then I'm going to tell you how we first implemented naive. And when I say naive, I just mean purely data engineering improvements. And still they were able to help us reduce processing time 60%. But we decided to move one step further and redesigned, re-architectured the whole thing from scratch. And we did it with help of HLL or Hyperlog Lock. And let me start telling you how we did it exactly. So EdTech stands for advertising technology. That's basically all the technologies and tools that help us to reach audiences, deliver and measure advertising campaigns. And here on this simple picture, I wanted to illustrate what are the three main doers in EdTech. Starting from the most simple one, we have advertisers. Basically, these are all familiar brands to you, like PepsiCo, McDonald's, Nike, etc. All the brands that are looking for advertisements in order to reach their target audience. Target audience are just simple people like we are, and we are watching some of the content that publishers produce. Usually publishers are some streaming companies like YouTube, Netflix. It can be TV programs, TV channels. It can be even some purely digital newspapers, wherever the content is published. And advertisers really want to spend their every dollar wisely. So it doesn't make sense for them to advertise luxury cars in the middle of some cartoon, like Disney cartoon, because kids are probably not the target audience and not buyers of luxury cars. That's why we need, as publishers, we need to integrate with advertisers to give them some kind of a promise how many people are going to watch the next season of Breaking Bad next quarter when we're going to release it. I made it up. of course, but that's the idea. So the main metric in EdTech is viewership, or in a very simple words, is just number of unique people who watched our content historically. And diving more into who our client is and their challenge. Speaking in terms of the previous slide, we are a publisher, so we produce content in other Netflix, YouTube, or digital media. You can think of us as all of that at once, and we are $30 billion mass media and entertainment corporation. They own TV networks, really famous and worldwide ones. They have their own film studio in Hollywood, they own streaming service, and they also have their amusement parks. And as I mentioned, they already had forecasting pipelines in place when we just joined. But the task was to optimize these forecasting pipelines so that they can run not in hours, but in just a few minutes. And forecast viewership for a given target may sound very complicated, but basically what we're looking for an answer: how many luxury car buyers will watch the next season of Breaking Bad? And of course, when we are talking about forecasting solutions, we use ML model. And this ML model produces forecast, but first it needs to be trained on some of the historical data. So we need to have some of the aggregated data for viewers on a daily basis, but not only all the possible viewers, but we need to limit them only to a specific target, meaning that we only need to predict the viewership for luxury car buyers or for pet owners. There can be hundreds of different targets in there. So how we get this time series data? Of course, we have in a blue, we have raw viewership history. So on a daily basis, we collect all the IDs, all the IP addresses, all the device IDs that we could possibly steal from you. And we merge this data with the target. However, the difference and the challenging task here is that while raw viewership history is available like all the time, it is cold data that we can pre-process in advance. Target we only get whenever a specific forecast is just triggered. So we literally have our marketing team, I'm gonna run the forecast for this target, and that is the moment in time when target is generated. So there is no way to know in advance how target would look like. And target here is just a huge, large list of IP addresses, device IDs, whatever we could collect from you. But they are kind of a segment because they need to tell us something about you. You're a student, or you're a luxury car buyer, or whoever you are. So when we just joined this project, we found this architecture, and we started from very naive improvements. Each of these elements in the diagram is basically a Spark Scala job deployed on EMR. And we started looking into the metrics of EMR, started looking into ways to improve the performance, and that really gave us very good results at the end of the day. And the first thing that we did was we moved from regular EMR to EMR serverless. And you need to understand that EMR serverless was only published as general availability several months ago. And we started this project several months ago, so it was almost simultaneously. And we decided to go for it because as you know, EMR cluster can start for maybe even tens of minutes. So it really takes some time. There is some delay in there. However, EMR serverless can start in seconds, assuming that you have some kind of a warm pool in place. But the limitation there was that EMR serverless only starts from a specific version of EMR, of Spark and Scala. So the first hands-on thing that we did, we upgraded Spark and Scala version of all the applications. And indeed, we've got a really good boost in performance. Also, we optimized instance types, number of executors, tuned some of the Spark settings, but I'm not going to dive deeper into the details, what exactly they were. That's not the topic of my, that's not the point of my speech today. The idea is that these pure data engineering improvements still gave us a very good performance improvement of 60%, but we decided to move further, and that is where math part is coming. So if you remember the design, the initial design that I presented, the bottleneck there was in this red target that we only can get real time ad hoc when the forecast is just triggered. We don't have this data in advance. And we started brainstorming the ways to still have some of the pre-processed data in advance so that we can run our aggregations on it in advance beforehand. And only in the middle of this pipeline, we would have our target to be appeared. Basically, the idea was that we need to move our target down in the pipeline to the right, to lightweight, to make the pipeline more lightweight. But even if we consider that there are some building blocks for the target, and we call them precanned segment, like the idea, there was still a big 2 question marks in here. Even though we have some of the pre-processed building blocks, how do we aggregate them in a way that target segments can be embedded in the middle of this pipeline? So they should have been somehow related. And that's the time when we need to start cooking. The idea here is very similar, and I'm going to explain this with help of borscht. So when you cook a borscht, you can either cut all your vegetables by yourself and then fry it, and it takes quite a bit of time. But instead, you can just buy some of the canned vegetables, which are already fried, prepared, and cut for you. And that would speed up the process of cooking borscht too much. So the idea really is the same. We're taking some of the pre-canned segments. So segments are groups of people that have some of the common features. It can be pet owners, parents, teens, luxury car buyers, etc. So pre-canned segments in our world are just some popular segments, and we prepare them beforehand in advance. And the idea is that we can then start cooking targets on the basis of these pre-canned segments, and the whole processing time should ideally be reduced. So luckily, we have smart people in our team, and they know what Hyperlog Lock is. I'm sure that some of you guys, especially data scientists, also met with this term. Hyperlog Lock is an algorithm or data structure, and its very simple goal, the only one, is to count unique values in a set. It's coming from a discrete math. And imagine we have a target. This is just a list, a huge list of IP addresses, and we need to count them uniquely. So the naive implementation here would be very memory consuming, because we need to memorize like each element and keep them unique to count only unique visitors, IP addresses. But Hyperlog Lock and its beautiful solution is based on the fact that we can use some of the probabilistic data structures that are not 100% accurate, but still they give us very good accuracy of 98%. But the beauty is here is that it only uses very few amount of memory, and complexity is so big from log n. That's why the Hyperlog Lock name came into place because of the complexity. And basically, since our main aggregation task was to just count unique viewers of our content historically, we decided that Hyperlog Lock indeed can be used for this metric. And also it works very fast for large gigabytes data sets. It works like for a few seconds. So that was the first thing that the first step in our architecture that we completely changed. And that's what we do. We identified the list of precanned segments that can be pet owners, drivers, people of 20 to 30 years old. This is some large number of segments. We started from few ones, but actually I see that in industry there are quite a few of them. So we take each and every precanned segment, and on a daily basis, we generate HLL, so Hyperlog Lock for each of them. And we store this history somewhere in S3 so that we can use it in future with our target segment. But the second big question here is how exactly do we use this HLL of precanned segments with the target? And here where the second nice feature of Hyperlog Lock comes from. Basically, HLL doesn't just gives you a number of unique visitors or IP addresses or whatever you count, but it can be serialized in some kind of data structure that have all the elements embedded inside inside it. And each element would have a hash code inside of this HLL sketch or just serialized internal structure of the HLL. And that's why we're able to intersect two different HLLs of two different segments or sets. And that was the idea of how we are going to target with our precanned segment. So let me dive into the next slide, which probably make more sense. So we are getting target ad hoc. We don't have it beforehand. Then we start generating HLL from this target, and it really takes just a few seconds to generate. But as you remember, for the ML job, we would need something that has time series attached, so some metric that we collect on a daily basis. That's why we collected the HLLs of our precanned segments on a daily basis. And now, whenever we already have our target HLL, we can intersect this target HLL with each and every HLL that we generated previously for precanned segments. And that, of course, gives us a time series that we can then supply to ML model. So that is the final answers on our two big questions. Target processing moved down to the pipeline so that the pipeline becomes more lightweight. And all the blue things we can prepare beforehand in advance. So that's our homework. We identified precanned segments and we process HLL, we generate HLL for each of these precanned segments on a daily basis. Then we run our join, aggregation, filtering, whatever, and it doesn't really matter already how much time does it take everything in blue, because whatever because the only thing that we are interested in starts from the target segment. And this one runs for really few seconds, few minutes, because HLL intersection is so effective. And we were able to embed it in the middle of our pipeline. So conclusion, we came to our client, we joined their team, we examined what they have, what pipelines did they run. First, we did some only data engineering improvements, and they already gave us like a 60% boost, which was really nice. And we did it by moving from EMR to EMR serverless, plus some additional Spark settings and removing some of the bottlenecks. But then we decided to consider alternative design that utilizes Hyperlog Lock. And then we implemented aggregation with help of HLL and intersection of these HLLs. And that all, in summary, could help us, was able to decrease the processing time from 2 hours to just a few minutes, 3, if to be the most precise. And that's all I wanted to share with you today. So if you have any questions, thank you so much for your time, and I'm happy to answer.
Okay, thank you, Daria. I can see a question. How the selection of precanned segments used influences the quality of the final prediction for the target?
That's a good question, because right now we implemented the whole thing as a pilot. Basically, that's a proof of concept. We didn't run it on production. We only launched in integration environment just to basically see how well it performs. And we was running our experiments on just several, well, I think 5 different precanned segments. So in terms of number of precanned segments, I don't have any metrics of accuracy, but there was one interesting thing that we didn't initially plan for. Basically, I mentioned that we have different types of IDs. Sometimes, let's say it can be Amazon ID, it can be IP address, it can be Netflix ID or whatever from different platforms that we own. And the thing is, HLL was not performing well in terms of accuracy because we were using these different types of IDs. They need to be homogenic, I guess. And we had to generate our own artificial ID so that HLL gave us better accuracy. So my short answer is we didn't test it yet with different precanned segments, but we tested with different ID types, and indeed it affected the accuracy.
All right, thank you, Daria. We have another question, which is this project deployed to production already?
No, it's not yet in production. Basically, it's currently in what we call integration environment. That's just some dev environment. And we started this project, I think, 4 months ago, and we weren't sure if the project would be successful at all or not. So it was really just a proof of concept. I'm hoping, though, that this effort will, at the end of the day, be converted to something production ready. But from the results that we have so far, it's really promising, and I hope it will be deployed one day to production.
All right. And another question is, what library did you use for the Hyperlog Lock?
Good question. I think in Spark SQL there is already implementation for HLL, but the thing is, it only produces you number, so long value. It doesn't give you the internal guts of HLL structure, of HLL sketch. And that's why using plain Spark SQL, we weren't really able to intersect. We wouldn't be able to intersect two different HLLs, and it was the essential part of our solution. So we had to use our internal library. And basically this custom library was already in place, implemented by the other team. Looks like the different department used it for their own purposes. And I know that it's a very common thing to implement, to solve tasks like count number of unique visitors for large companies like Google or Amazon, because HLL does it pretty fast on the fly and requires little memory. So I assume that this other department used it for a similar but a little bit different purposes. So it was a custom library.
Okay, and we have one more question. I will do my best to read it properly because it's a long one. Could you please explain in more details how ad hoc target is being transformed into Hyperlog Lock structure to be intersected with the pre-cooked HLLs?
Whenever we get our target, and target is just a list of IP addresses, device IDs, any kind of identifiers, we immediately run this whole data set through the HLL library that I mentioned. So there is a way to insert each and every element to this library, physically one by one, or in Spark, that all happens in parallel. And as a result, you don't just get long integer value, but you can serialize it to bytes, and that gives you all the internal structure, all the hashes of each and every element. And also in this custom library that we used, there was already implemented for us a function for intersecting two different HLLs, and that gave us the third HLL basically, and this one in turn could give us already a number.
Okay, thank you. I don't see any more questions. We can wait for another 10 seconds. Maybe someone wants to. Okay, if you come up with a question later, I think after Rinat's speech, we can come back to Daria's answers. So now it's time to go on, and our next speaker is Rinat Akhmetov. So please, Rinat, you can start.